Okay.
How should I say? If I feel free to interrupt me or
Okay.
my sentences.
Okay.
So let me know when you're ready. It's so awesome that our tradition of Perry lectures keeps going, and Bill Perry established a fund from which his lectures are supported. Bill Perry was the president of Eastern Illinois University and a professor in the mathematics and computer science department. Today's speaker is Boris Reznik, professor of mathematics from the University of Illinois, Urbana, Champaign. And I met Bruce when I was a student in Urbana, and I am indebted to learn so much about mathematics and teaching mathematics from Bruce. And I don't want to stand between you and the speaker anymore. So Bruce, the floor is yours.
Okay.
So thank you so much.
Thank you. The first thing I want to mention is that I met Bill Perry in May when he gave the speech at the math department convocation ceremony in Champaign, Urbana, and I had no idea I was going to be giving this talk, or I would have tried to get some advice from him. So to start the talk, 2022, 2023. How many people here have ever counted to 2023? I was doing it this week by hundreds because otherwise you get lost. It's a big number, but it's not an impossibly big number. For example, I'm not very good at this, but these are roughly 3 feet by 5 feet. Or imagine these are 3 feet by 5 feet. If they're 3 feet by 5 feet, then each one of these has 2,160 square inches. So if you can imagine it divided up very finely, that's what 2,000 is like. I made a list here. 2,023 seconds is 34 minutes. 2,034 minutes ago was about 9 a.m. yesterday. 2,034 hours ago was August 3rd. 2,023 weeks ago was the week of the Reagan-Mondale election. 2023 months ago was a couple of years before the Lincoln-Douglas debates. So it's a big number. I did some playing on the internet. 2023 Cheerios is about 8 ounces. 2023 grains of rice, depending on where you look, is either somewhere between 1 ounce and 2 ounces of rice. So you see 2023 all the time. For baseball fans, Scott Rowland, who just got elected to the Hall of Fame, played 2,023 games at third base. For Cardinal fans, Albert Pujols played 2,026 games at first. And of course, a lot more as a designated hitter. And Ted Williams had 2,021 walks. So there are these counts. This indicates you do it for a while. To give you a more vivid example, and I'm glad I have 4 colors. Imagine a 2-letter code where you pick any of the 26 letters. There are 676 of these codes. Now imagine this where you have 3 possible colors. Let's say LE and U. How many different ways can you pick a 2-letter code with one of 3 colors and 2 letters? And it's 3 times 676, which is 2,028. So it's really not that hard to visualize what 2000 is. For those of you who are taking number theory or teaching number theory, 2023 is a good number for number theory problems because it factors very nicely as 7 times 17 squared. Okay, 2023 in Roman numerals, I hope I get this right, is MMXXIII. Now, Roman numerals were used for a very long time before the more common Arabic Indian system that we use now. And one of the big influences on that was the increase of trading in the middle of the last millennium. There's a very interesting book called Arithmetic and Capitalism, which contained a story in which a German businessman asked a professor where he should send his son to be educated to do enough mathematics in order to become a trader. And the professor replied, if all he will need is addition and subtraction, then it's okay to keep him in Germany. But if he will need multiplication and division, you should send him to Italy. And I think one of the virtues of there is that it shows that arithmetic is not automatic. But we can do things more easily using a common system. And what 2023 really means, in a literal sense, is 2 times 10 cubed plus 0 times 10 squared plus 2 times 10 to the first plus 3 times 10 to the 0. And for those of you who are not familiar or are a little out of practice, n to the 0 is 1. And n to the 1 is n. So we can write any number in terms of the ordinary decimal notation. And being a mathematician, I'm going to make a slightly messier version of exactly the same thing. I hope this is, if anything is not legible, please let me know. To a mathematician, this statement and this statement are complete synonyms. And it sometimes is easier to write things like this, but this is what I really mean. And I'll try to go back and forth between the two. Now, we work in base 10 because we have, or generically, we have 10 fingers. It makes it easy to count. But, and I don't know if they teach this anymore. If b is any integer greater than or equal to 2, and n is greater than 0, we can write n as a0 plus a1 times b plus a2 times b squared up to ak times bk for some k. And this is important, that the digit set is the integers that are strictly less than b, including 0. And I don't know if this is taught in schools anymore. B equals 10 is something that's completely familiar. B equals 2 is binary. B equals 12 is a system called duodecimal, which had a fad in the 19th century. James Garfield, the president, was a member of a society that wanted to change our number notation from 10 to 12. Did not work. How do you do it? Well, I don't think it's appropriate in a talk like this for me to give anything like a proof. So instead, let me give you a procedure using only familiar ideas. So you take your number n. First of all, if n is small, you just make a0 equals n, and you're already done with nothing, and k equals 0. So 7 is equal to 7. If n is bigger than b, you do division. You just take your number b, divide it into n. You have a remainder that's less than b. This is something I believe you're still taught in elementary school. And then you do the same thing to n prime and so on. Let me illustrate that with 2023. I can see I'm going to have to start erasing things, if that's okay. There's no chalk dust. That's the one advantage of whiteboards. 2023 is 10 times 202 plus 3. 202 is 10 times 20 plus 2. 20 is 10 times 2 plus 0, and 2 is 2. I hope it's clear what I'm doing. I'm taking this expression each time and moving down one level. So now 2023 is 3 plus 10 times 202, which is 2 plus 10 times 20, which is 0 plus 2 times 10. And if we expand out all the parentheses, this is 3 plus 2 times 10 plus 0 times 10 squared plus 2 times 10. There are 3 of them there, 2 times 10 cubed. And what I've said here would work for any base other than 10, but since it's already past 6 o'clock, I'm not going to try to, and there won't be a test. I won't show you what happens if I pick a number other than 10. But this works in a completely general way. I have another one which I'll be using a little later. We take a different color. Let's take 128 and 3. 128 is 3 times 42 plus 2. 42 is 3 times 14 plus 0. 4 is 1 plus 1. And then this translates into saying that 128 is 1 times 3 to the 4th plus 2 times 3 cubed. Did I miss one? Plus 0 times. Who wrote this stuff? Where did I make a mistake? Anyway, if somebody does this correctly, 128 is 1 times 3 to the 4th plus 1 times 3 cubed plus 2 times 3 squared plus 0 times 3 plus 2. I think I skipped something somewhere and I don't remember what I did. It doesn't matter too much, but this is an illustration of writing 128 in base 3. Fortunately, I no longer have to worry, since I'm technically retired now, I no longer have to worry about course evaluations. So let me give you a puzzle that you sometimes find. I don't know how well known it is. Suppose you have a balance beam and you have 3 weights, and the weights are the powers of 3. 1, 3, and 9. In grams or whatever your favorite unit is. How many different things can you exactly measure with this? So if you wanted to measure 10, you would have a complete balance. If you had a 10 gram weight over here, and then you matched it with the 9 and the 1. If you wanted to do a 7, it would be a little trickier. You'd have to put the 3 here, and you would still have a balance like that. And the fact is, when this problem is presented, every weight between 0 and 13 can be gotten exactly once. And is this a familiar thing to people? Maybe to math people, not to non-math people. But you might be wondering, why am I talking about balances? What does this have to do with the talk? And the answer is, the first statement is that 10 is 3 squared plus 3 times 0. The second one is that 7, if you move the 3 over to the other side, that 7 is 3 squared times 1 plus minus 1 times 3 plus 1 times 3 to the 0. And this suggests another way of writing numbers that's not the basic base 3 system. And in fact, it's in my contract that I have to use the word theorem at least once. Every integer n can be written as n equals summation I goes from 0 to some m of ai times 3 to the I, where ai takes the values minus 1, 0, and 1. This is not the standard thing. This is an old theorem. This goes back to the 19th century. And I'm going to give you two proofs, or two things that could be turned into proofs. These are not given in the diction of a proof, but just as an indication of the proof. And to illustrate this, let me illustrate this with my pathetically mistaken example 128. Which you may notice fails the test here because there are a couple of 2's. What you do is you take your number and then you add all of the powers of 3 that you can think of going up to a certain point. And that's 128 plus what turns out to be 121, which is 249. And because I did do this in advance, this is actually 3 to the 5th plus 2 times 3. 243 plus 6 is 249. So you might wonder, big deal. Let me write this as 1 times 3 to the 5th plus 0 times 3 to the 4th plus 0 times 3 cubed plus 0 times 3 squared plus 2 times 3 plus 0. Well, I added something to 128. Let me take it away. So 128 is 1 times 3 to the 5th plus 0 minus 1, 3 to the 4th, plus 0 minus 1, 3 cubed, plus 0 minus 1, 3 squared, plus 2 minus 1, 3, plus 0 minus 1. In other words, 3 to the 5th minus 3 to the 4th minus 3 cubed minus 3 squared, plus 3 minus 1. And that's a way to write 128 as the sum and difference of powers of 3. This works in general. If you're a mathematician, you'll see how to generalize this for any odd integer, an odd integer 2n plus 1. The digits go from n to minus n. You can do a lot of things with this. What I'd like to do also, because there are many people who are visual thinkers rather than algebra thinkers, maybe even a majority, there is a visual proof of this that appeared in a dissertation by one of my recent students, Dana Neidman, who is currently teaching at Centre College in Kentucky. And that is, think of sort of a dynamic process where you start out with a number that has this strange format. And then you think of taking the digits you've written and shifting them over by 1. So 3n is a0 times 3 plus a1 times 3 squared up to ak times 3 to the k plus 1. Now, if these are all minus 1, 0, and 1, these will all be minus 1, 0, and 1. But now, if you're lucky, you can see that we actually get 3 possible numbers, depending on what we put in here. We could put in minus 1, we could put in 0, we could put in 1. So in the language of directed graphs, forgive me, if you get n, you can get 3n minus 1. If you can get n, you can get 3n. If you can get n, you can get 3n plus 1. Let me draw a picture of this. The eraser works. So you start with nothing, and then you multiply nothing by 3, and in the first stage you can get minus 1 or 1. In the next stage, you multiply by 3. I'd have to spread these out a little bit. And remember, each time you multiply by 3, you can get something 1 less or 1 more. And this just keeps going. And you can probably believe that you're going to get a consecutive set of integers going from something to something else, and that something is increasing as you go down. So eventually you will get every integer in there. And as I said, this was from their thesis, and that's another way to visualize it. A lot of digital type questions can be put into graph formats. So now I want to go to a little trickier thing, which is everything that I've shown you so far has a number has a unique representation. But what if you go to borrow a phrase from one of the great mathematicians who influenced me when I was growing up? What if you go on beyond zebra? If you go beyond the standard alphabet, if you allow more digits, the references to Professor Seuss, of course. Suppose you want to write n as in binary. But now you're going to allow 10 as a digit as well as 9. Well, it turns out that there actually are 2 ways to write 2023. I've already written one of them. The second way is this. Now, one of the things mathematicians might want to do would be to count the number of ways you could write a number in this way. What if you really went on beyond zebra and wanted to go up to 99? Now, it turns out this is a question that I can completely answer, and I hope to be able to persuade you that the number of representations of 2023 with the digits going from 0 to 99 is exactly 203. What's 203? Well, that's the number of integers in the set from 0 to 202. So now, even though I have failed at doing arithmetic in real time, I'm willing to try it again. And I will request a number between 0 and 202. Somebody?
117.
117, okay. So 117 And this is, I believe, 853. And that's because when I was a kid, we didn't have calculators. If we wanted to do arithmetic, we had to do it ourselves. Assuming I've done this correctly. So, what is 117? That's 1 times 10 squared plus 1 times 10 plus 7. Now I have 10 times 117. But rather than work on the powers of 10, I'm going to work on the coefficients. And now I have the leftover, which is 853. That's 8 times 10 squared plus 5 times 10 plus 3. And if you add this up, you get 18 times 10 squared plus 15 times 10 to the first plus 73. And I hope you will take my word for it that every representation getting these up to 99 can be found in exactly this way. And you can work backwards because if n is summation ai 10 to the I and ai is between 0 and 99, then ai is 10 times bi plus ci, where bi and ci are the usual digits. Now, if you happen to be in the very arcane subject of studying the Putnam math competition, there was a problem very similar to this on the I think it was the 1982 exam, only with 2 rather than with 10. Looking at representing numbers in binary with the digits 0, 1, 2, and 3. And I put that on the exams. So I was kind of pleased with that one. Now, the next thing you might ask is, what happens if you make no restriction on AI at all? You just make the AI be integers greater than or equal to 0. And combinatorial mathematicians have and number theorists have a subject called generating functions, which lets you calculate the value exactly, or at least have your machine calculate the value exactly. And my machine told me that there were 2,749 different ways to write n. In looking at my notes, let's see. Did this fall off something important? I'm sorry? It's okay. Okay. I'm not used to this technology. I actually asked Mathematica to give me 2023 written in all of the bases that you can do. Now, computer scientists are very interested in writing integers base 16 because that's a way of compressing binary digits 4 at a time. And they don't want to write 10, 11, 12, 13, 14, and 15. So they generally use A, B, C, D, E, F. Well, if you think about it, this gives 26 potential additional letters. And the Mathematica command base form works exactly up to base 36. So 2023 is in binary. Binary is kind of fun, actually. It's 111, 111, 00111. For those of you who've worked with computers, that certainly looks like a binary number. In base 3, it's 2202221. In base 11, it's 157A, which means this is really 10. And in base 17 is really nice. That's because, as I said earlier, 2023 is 7 times 17 squared. So that comes up very nicely in that representation. Okay. Okay, so I've got about 15 or 20 minutes left, and I'll be sort of changing the subject, but not completely. There's a particular choice of digital representations that relates to a part of mathematics that I've had a lot of fun playing with over the years called the Stern sequence. So let me first give you the situation, and I hope you'll recognize this as similar. I want to write n in base 2 and I want to go with 0, 1, or 2. And I'm going to let f of n be the number of ways to do this. So let's take a quick example. If I start with 2023, I want to write it like this. The left-hand side is odd. So there's only one choice for A0. This all is even. A0 is in 0, 1, or 2. So A0 has to be 1. 2023 minus 1 has to be A1 times 2 plus A2 times 2 squared, and so on. And if I divide it by 2, what this tells me is that f of 2023 is actually f of 1011. I could keep going like this, but I don't want to use up the time. It's a little different if n is even. Let's take a simpler example, f of 6. So if you wanted 6 to be a sum of powers of 2, you can sort of stop there because everything else is going to be bigger. So A0 has to be even. If A0 is 0, we get that 3 is A1 plus A2 times 2. Or if A0 is 2, then we get that 2 is A1 plus A2 times 2. So to put it in the language that mathematicians would like to say, f of 2n plus 1 is f of n. F of 2n is f of n plus f of n minus 1. And this is a form that computers like working in. This is called a recursive formula. You need to put in some basic initial conditions, and you can calculate it out as long as you want. OK, keep that in the back of your mind. One of my favorite mathematicians was named Moritz Abraham Stern. He was a German mathematician in the 19th century. And he came from Frankfurt. He was from a family of rabbis who wanted him to be a rabbi, but he wanted to be a mathematician. He went to Göttingen, and he got a PhD, and his advisor was Gauss. Let me emphasize, this is not somebody who thought he was Gauss. This was Gauss. He was, in fact, Gauss's first PhD student. And he stayed on at Göttingen, but the problem was that under the laws of the time, someone who was Jewish could not be a state employee. So he made his living for a long time from the fees that students paid to attend his lectures, which gave him a motivation to being a really good teacher. And he was also famous for keeping up with his students after they finished. Among them were people that mathematicians know, like Riemann and Eisenstein. And eventually the laws changed. And in 1858, he became, well, if you were Jewish, you could be a professor if you got baptized. And he didn't want to do that. In 1858, he became the first Jewish full professor in any university in Germany in any subject. His son was a historian who taught at a university in Switzerland. And late in his son's life, his son befriended a young Jewish university student named Albert Einstein. And if you look at Einstein's letters, there are a lot of letters between him and Stern's son. And it's wonderful to me that you can get from Gauss to Einstein with a father and a son, where each of these connections is a really strong connection. Now, it's 100 years, but it's still kind of like that. So what did Stern do? Well, there's a genre of mathematics I like to call airplane problems. Suppose you're stuck on an airplane, no Wi-Fi. All you have is a piece of paper. What sort of math can you do with that? And the Stern sequence is very much like that. How could you start with anything easier than 0 and 1? Those of you who know Pascal's triangle know that what you do is when you see two numbers, you write the sum in between. But in this case, you keep writing the numbers that you started with. So it's like a Pascal's triangle with memory. Let me go to the next row. You have 0, 1, 1. I'll spread it out a little bit. 0 plus 1 is 1. 1 plus 1 is 2. And there are an enormous number of properties you get. One of the properties is that the first row, each row is the first half of the next row. Another property is everything's an integer. For those of you who know a little number theory, the next property is that any two of these integers are relatively prime. And the next property that Stern noticed is that if you write down the fractions, and you keep going, he proved that every positive rational number occurs exactly once in this sequence. Now, to modern math students, this would be saying that the rational numbers are countable. Stern did not say that the rational numbers were countable because he was doing this in 1855, which is 30 years before Cantor defined countable. So this is an example of a theorem that came before its time. And what's more, this is really nice. Don't think I want to. Well, okay, I'm going to ask for two numbers that are relatively prime that are not too big.
Say that again.
Two numbers that have no common factor but aren't really huge. Okay, well, let's see what we can do with that. Let me put it in the order 50 and 17. Okay. Now, mathematicians use something called continued fractions. 50 over 17 is 2 plus 14 over 17. No, it's 2 plus 16 over 17. That'll actually make it easier. This is 2 plus 1 over 17 over 16. This is 2 plus 1 over 1 plus 1 over 16. And when you study continued fractions, often you're looking at convergence of an infinite continued fraction. I'm talking here about a finite continued fraction. And I was also fortunate enough, as it turns out, that there were an odd number of denominators here. So the theorem, and this was discovered in the 19th century, is read these numbers backwards. 16, 1, 2. Write the number 5, 6, 7, 8, that has 16 ones, no zeros, and 2 ones. And look at the number which has this binary representation. So this is going to be a number, it's in the hundreds of thousands. I don't want to try to work it out right now. But the theorem says that if this is the number n, then S of n is 50 and S of n plus 1 is 17. So not only for the experts in here, not only is this an enumeration of the rationals, but there's a very easy way, there's a very easy encoding of the rationals, so you can find out where any particular rational is. And that's just a lot of fun. And the connection between these two, if you write down this sequence, S of 2n is S of n, S of 2n plus 1 is S of n plus S of n plus 1. And then this is the number of ways to write n minus 1 in this weird case with allowing zeros, ones, and twos. And looking at the Stern sequence is what got me interested in looking at these odd digital cases. So let me give you a shortcut to finding the sequence, because you probably don't want to have to repeat the first half. If you start with just 1 and 1, then you will always get the second half of the sequence. And there are a lot of nice properties. The sum, if you add a sum across the rows, this is 2, this is 4, this is 10, 8, 13, 15, 20, 28. Anybody recognize the sequence? That's 1 plus the power of 3. That's something that can be proved. What about the largest value? I'll underline it. 2, 3, 5. Any number theory fans here? Any Fibonacci fans here? Care to guess what the next big record is going to be? It's going to be 8. In fact, it's going to come right here. And 8 will be next to 5, so the next row you'll get 13. And this is the way the maxima go through. I think I have 5 minutes, so I'd like to go back to something that we did earlier. Every integer can be written uniquely in binary. I would claim this is the most valuable mathematical theorem that has ever existed. This is a $1 trillion theorem. The entire computer industry is based on the fact that you can write numbers uniquely in this way. So I'll take credit for it. It's not my theorem. And let's see. I've gone a little faster than I thought, so if there are any questions, I think now is a good time to take care of them. Yeah.
Would you mind telling us where else this beautiful sequence is used?
Okay. There's a following interesting construction where you start with a triangle, and then you trisect the sides, snip off the corners, and you go from a triangle to a hexagon. Now, if I use vector notation for this being u and this being v, if u and v are consecutive vectors in the main triangle, after I cut them, since these are all in thirds, I have u over 3, u plus v over 3, and v over 3. If I did it the next time, it would be u over 9, 2u plus v over 9, u plus v over 9, u plus 2v over 9, and v over 9. And if you forget the powers of 3, because we're interested in the shapes of these curves, the coefficients of u go 1, 0, 1, 1, 0, 1, 2, 1, 1, 0. The coefficients of v are, at this point, depressingly familiar. And in fact, historically, Stern did not think of the Stern sequence as a sequence. He thought about it as starting with two numbers a and b. But if you do that, you can quickly persuade yourself that all of the coefficients can be derived from the coefficient of this one over here. And this was the first time somebody actually isolated the sequence. This was in the 1950s. I've forgotten the name. A very distinguished French geometer did this. And there is a wonderful resource called the Online Encyclopedia of Integer Sequences. If you are a graduate student, you definitely should know about that. If you run into a sequence, you can just look it up in there. It used to be a hard copy book. And I looked up the sequence that I had been playing with in the book, and I found a reference to this. And so that's one instance where it comes in. You can look at the recurrences at the sum of the squares of the elements in an entry, the sum of the cubes of. I'm in theory writing a book on this, but I've been doing that about 20 years. So it's endless fun. And speaking of endless fun, I think I should stop. Thank you for your attention. And if you have a question that you don't want to have filmed, once they stop filming, I'll be happy to answer it.